atmospheric boundary layer is the lowest part of the atmosphere that dictates the transfer of energy, moisture, and momentum between the Earth's surface and overlying atmosphere. Understanding the processes that impact atmospheric boundary layer structure and stability is important to reveal how much the surface and atmosphere interact with each other under different conditions. This is particularly important in the central Arctic, where the atmospheric boundary layer is a thin border between a retreating and thinning sea ice pack and a rapidly warming atmosphere. To determine the forcings which interact with the atmospheric boundary layer in the central Arctic, we utilized data from the Mosaic expedition, a year-long ship-based campaign. Our research revealed that two primary drivers of atmospheric boundary layer stability in the Arctic are mechanical mixing, which depends on wind speed, and thermodynamic mixing, which depends on the surface radiative fluxes, such as downwelling long-wave radiation. So how do we know what the stability of the atmospheric boundary layer is? One common method is to look at the observed profile of virtual potential temperature. Potential temperature increasing with altitude signifies a stable atmosphere, where fluxes of energy, moisture, and momentum occurring at the surface will be constrained there. Potential temperature staying constant with altitude signifies a near neutral atmosphere where these fluxes are well distributed throughout the layer. And potential temperature decreasing with altitude signifies an unstable atmosphere, but this is almost never observed in the central Arctic. In the absence of mechanical and radiative forcings, the Arctic atmospheric boundary layer is inclined to be stable when the highly reflective sea ice surface and clear skies results in surface heat being lost to space, such that the surface is colder than the above atmosphere, as depicted by the leftmost line plot. This type of stability was observed 27% of the time during Mosaic. When enhanced surface downwelling long-wave radiation is introduced, usually due to the presence of a low cloud, but wind speeds are still minimal, a shallow near-surface layer will become well-mixed, as depicted by the line plot second from the left. This type of stability was observed 27% of the time during Mosaic. Now, if this source of enhanced downwelling radiation dissipates, but the elevated wind speeds are introduced, for example, in the presence of a low-level jet, then the atmospheric boundary layer will be mixed towards being weakly stable throughout a deeper layer, as is depicted by the line plot second from the right. This stability was only observed, however, 9% of the time during Mosaic. This is because usually when there's enhanced near-surface wind speeds, there's also clouds which cause the elevated levels of downwelling long-wave radiation, and the atmospheric boundary layer becomes near neutral through an even deeper layer, as depicted by the rightmost line plot. This type of stability was observed 37% of the time during Mosaic. In all examples, there's a layer of stability somewhere within the lowest 1 kilometer of the atmosphere. Therefore, while the surface-atmosphere interactions can extend through a deeper layer when mechanical and radiative forcings are present, there's also always eventually a decoupling of this near-surface layer from the atmosphere above, making the Arctic atmospheric boundary layer unique compared to that of the mid-latitudes, and partly explaining why anthropogenic warming has an enhanced impact on atmospheric temperatures in the Arctic.